And we are set. So yeah, last time we had just kind of drawn out the P versus T diagram, the phase diagram for water, H2O. I guess water is just the liquid phase, but I always just call it water. So yeah, we just kind of emphasized the point that this is negatively sloped right here, and that's unique to water. We talked about all the definitions of what vapor pressure means, what the triple point means, what the critical point means. So I think we're about good with that. Let's see, what else do we have to talk about? Oh, yeah. So one key thing to talk about, you might say, oh, there's a critical point here. Is there anything where there's like a similar notion of a critical point where you can't distinguish between the phases for like the liquid phase of something and the solid phase or the gaseous phase and the solid phase? And the answer to that is just no, because the point here is that like water and steam are qualitatively similar in that the molecules can freely move around. They're not locked into some kind of like lattice structure. So you can reach this kind of critical point where you get this blending between them. But no such thing exists for the boundary between like solid and a liquid and solid and a gas, just because they're qualitatively different. So you'll never see a critical point like this existing between these other phases. Okay. Let's see. So we can look at another example of a very interesting phase diagram. So that is of helium. And so there are two isotopes of helium that are commonly found. And so one of them is 3He, which is the rare form, not commonly found. The other one, for helium, which is common. Do I have these flipped around? Give me a sec. Yeah, I have these flipped around on my notes. Okay, so this one, its phase diagram looks something like this. Whoop. Shoop, oop, doop. So up here, have so-called solid helium. Over here, we have helium-1, which is the first liquid phase. So we think of this as just like a normal liquid with no unique properties. Over here, we've got our gas. Obviously, this is a critical point akin to what we were talking about with water. So at that point, the two phases blend together. And helium also has this interesting phase right here, which is called helium-2, which is a so-called superfluid. And no, it doesn't mean that it like fights crime and takes out all the villains and whatnot. It means that it has zero viscosity and a very, very, very high thermal conductivity. So this is just a really interesting state of matter. We're not really discussing any kind of quantitatively calculable features here. We're just discussing rough qualitative stuff. So these are all PT diagrams, just so you're familiar with what things look like here. So the rare form of helium looks something like this. Shoop. And that, so it's similar. And it actually does also have a superfluid phase, but it is like way down in here. So it's like in this region right here. There's actually two of them hidden in this little tiny region right here at very low temperatures and very low pressures. So I think those are like less than like 3 millikelvin. So we're talking low, low, low. So another interesting thing to notice about helium in general is that all the way down to 0 Kelvin, it's still a liquid. I mean, typically you would think of things as if you've extracted all of their energy such that their temperature is 0, they turn into a solid. But helium is unique in the fact that it is liquid all the way down. So that's all we have to really say about that. And you can research more about superfluids if you please. There's some really interesting videos on YouTube I'm sure you could look up where you can see like containers of helium where it just kind of like crawls up the side and like comes out of the container all on its own because it has zero viscosity. It's wild stuff. But another thing we want to note here is that temperature and pressure are not the only variables that affect the phase. So T and P, not the only. So these aren't the only two things that you can change that affect the state of matter. Does anybody have any thoughts about what some other variables are that you can change for a system that can change its phase? Is there one big one that people are throwing lots of money into so that they can make energy transfer a lot more efficient? Superconductors, right? Anybody familiar with superconductors? So basically, superconductor is a material that has a phase diagram that looks like this. So this is the magnetic field applied to the superconductor. This is the temperature of the superconductor. So this is the external magnetic field. And right here, at this point, we have the so-called critical magnetic field. And here's the critical magnetic temperature. And so phase diagram looks something like this. And out here, you've just got regular old material. And in here, you have a superconductor. And so these are called type 1 superconductors. All type 1 superconductors have a phase diagram that looks something like this, where it's just got one normal phase out here and then a superconducting phase inside of this critical boundary. Type 2 superconductors aren't talked about in the book, but they're basically just type 1 superconductors with an extra line right here. And so then in between those two phases, you have superconducting. So that's that, and some examples of type 1 superconductors are tin, mercury, and lead. And the problem is typically that in order to actually get these things into their superconducting phases for normal materials, you have to be at super, super, super low temperatures. And so they're not entirely practical for real life applications because you have to keep them so cold all the time. So there's a lot of money and research obviously being invested in making like room temperature superconductors. So if you're looking for a field to go into, that's a big one for sure. Another interesting thing is the ferromagnet. Does anybody have an example of something that behaves like a ferromagnet? Type of material, an element? Surely somebody. Oh, I see something in chat. Yeah, Deb's got it. Iron. Iron's a good example of this. Yeah, iron. Okay, so again, one of the variables that we can change is the external magnetic field. Basically, if you apply some magnetic field positively, you can get it into a phase that looks like it's magnetized in the up direction, which means all of the little spins in this ferromagnet are pointed up. And if you apply an external magnetic field in the minus direction, they'll all magnetize down. That's pretty straightforward and intuitive. On this axis here, we have temperature. And what was actually shown is that there's a certain temperature here, which acts as another kind of critical point, where these two phases are no longer distinguished together. And so the way I like to think about this is that basically if you're at really low temperatures, if you're at zero temperature, for example, the spins, like the particles in this ferromagnet, they're not jostling around at all. So if you apply a magnetic field, they'll just automatically align to whatever direction the magnetic field is going. As you increase the temperature, at some point, the amount of thermal energy that you get, the amount of jostling that occurs, is actually able to randomly orient the spins themselves. So at some point, you reach a hot enough temperature where they jostle so much that they can't be magnetized up or down. They just kind of blend together. So that's how I like to think of that. The critical point is also called the Curie temperature. after, does anybody know? Does anybody know which Curie this is? I actually didn't write down the first name. Yeah, it's Pierre. That's right. Yeah, so this isn't the good old Madame Curie, who everybody knows and loves. This was actually her husband, Pierre Curie. And does anybody know, this was a little interesting tidbit of info that I found on Wikipedia. Does anybody know how he died? Because we all know that Madame Curie, and maybe you don't know, but also her husband, they were both really heavily involved with understanding radioactivity, right? But the problem was, if you're the first person to start learning about radioactivity and you don't know whether it's dangerous or not, you subject yourself to a lot of radiation, and you're surely going to die of that. So that's obviously a tragedy. But he didn't actually die of radiation poisoning. He died of getting run over by a horse-drawn carriage trying to cross a street. So actually not a horrible way, honestly. It could have been a lot worse, because yeah, dying of radiation poisoning doesn't really sound like a pleasant way to go. So just a fun fact. All right. Now we have a discussion of diamonds, everybody's favorite so-called valuable material. Not really valuable at all. And graphite. So what we know is if we take elemental carbon, it has two familiar phases, which I just wrote. It has a phase that looks like diamond, and it has a phase that just looks like, sorry, not carbon. I wrote carbon in my notes. It's carbon. Graphite. Sometimes I don't think when I'm writing these notes. And so graphite is actually more stable at ordinary temperatures that we exist at. Ordinary TNP. So this is something that's embarrassing. Yeah, I know. I do a lot of embarrassing things. You get over it when you do it all the time. So yeah, this is something that jewelers don't discuss a whole lot, is that diamonds are actually less stable than graphite. Granted, the amount of time it takes for graphite to turn in, or diamond to turn into graphite, is crazy long, which we'll say in a little bit, but that's something people don't normally talk about. So what we're going to ask now is, how can we understand the stability difference between diamond and graphite in terms of what we learned so far? Okay, so what we learned in a previous section is that we can re-express the second law of thermodynamics as this. We just talked about this in the quiz too. And so the second law becomes that you want the Gibbs free energy to decrease, right? So if we look at page 404, then you can find that for graphite, this is just 0. And for diamond, it is 2,900 joules for 1 mole of each substance. So obviously we have that delta G graphite is less than delta G diamond. And what does that imply if we're using the second law in this form? What does that tell us? So if we've got carbon, we've got 1 mole of it in one state, 1 mole of it in the other state, or phase, I should say. Which one of them is going to be more stable? So the second law says that it should, the entropy should increase overall, right? And that means that this should decrease. So whichever one of these is going to be lower is the one that's more stable. Yeah, so it'll tend towards graphite. Yeah, everyone's getting it now. Yeah, so graphite is tended toward. So we got that. So this is all for just our standard environment, which is 298 Kelvin, 1 bar. But you could ask, what about at other temperatures and pressures, right? So here's what we can do. We can hold, no period there. We can hold the temperature and the number density constant for the time being. And then we have that from our thermodynamic identities for G, we could write that the derivative of G with respect to the pressure, holding T and N constant, is the volume. So basically this tells us that if we know the volume, we know the slope of G with respect to the pressure, right? So again, if we look in the back at page 404, we can write down the volume subtended by 1 mole of graphite and 1 mole of diamond. And so for graphite, it is 5.3 centimeters cubed. And for diamond, it is 3.42 centimeters cubed. So therefore, what do we have? We have that the slope for graphite is actually bigger than the slope for diamond with respect to pressure, right? So if we were now to plot this, what would we have? We have G here, we have P here. So we know that at like room pressures, which we'll just say start right here. So this is like 1 atmosphere. That at that point, we have that graphite is more stable. So graphite's down here and diamond is above it. So diamond is up here. So this is like the starting point. But so now if we look at this relationship, it tells us what the slope is if we know the volume. Well, the slope for graphite is bigger than the slope for diamond. So that means that qualitatively, it has to look something like this, right? So this slope's going to be something like that. This slope's got to be lower. So at some point, mathematically, they have to intersect, right? There's some point of intersection in the future. So what does that tell us? What does that tell us about anything to the right of this critical point right here? Anybody have any thoughts about that? How does that change what we were just saying about the stability? Yeah, Saif, you're exactly right. So after they cross, obviously diamond is now at a lower Gibbs free energy, and so thus it's the more stable state. So effectively, what you could do if you were the first person to figure this out, you could find out what the critical pressure is. You could be like, oh, well, I know roughly the density of like the top layers of the earth or something. I'm going to determine exactly how deep down I need to dig in the earth in order to get me some diamonds and sell them for a bunch of cash, right? So maybe, yeah, Saif would do that because he's really wanting to make some money for himself. He wants his Lamborghini or something. I don't know. And so it ends up that, oh, let's see, I think they form naturally at like 50 kilometers down. So you would have to dig pretty deep. So I would not recommend doing that. Let me just write this. So this is the dividing point over here. I guess it's worth it. I don't know about that. Graphite more stable. Diamond more stable. Yeah, I mean, the only reason people even want diamonds is because they're supposed to be in short supply, but we can actually make them in a lab, so I'm injecting my own opinions about stuff. Shouldn't do that. Okay, so we can do the same thing for temperature dependence. Never thought diamonds were perishable. Yeah, I know, me too. Well, I mean, I knew that, but I had never thought about it in a while. But it turns out, where did I write this? Yeah, so I was gonna say this later, but at room temperature, the time it takes to turn diamond into graphite in room pressure, it's like greater than 1 billion years to turn 1 cubic centimeter of diamond into 1 cubic centimeter of graphite. So they're effectively not perishable. But on the real physics. So if we do the same thing for the temperature dependence, so we hold the pressure and the number density constant, then we can get this relationship from the thermodynamic identity for G. If warehouse is full, then won't see. Yeah, diamond is a prime example of just artificially manipulated prices. but there's lots of stuff like that. So we can get this thermodynamic relationship from the thermodynamic identity for G. We're getting into like economics now, so let's get out of that. I'm not an economist. Okay, so we know that now the slope of the free energy with respect to the temperature is dependent on minus the entropy using just the thermodynamic identity. So we need to look up what the entropies are, but before we look it up, let's just ask ourselves, do we think that the entropy for diamond or the entropy for graphite should be greater? Which of them should be bigger, do you think? Which of them is more ordered? Thoughts about that? So yeah, intuitively, diamonds are an incredibly ordered substance. And so they actually do have a little bit lower entropy than, does that depend on T? Yeah, I mean, well, no. Yeah, it would depend on T. Yeah, so yes, the entropy would depend on T. I'm talking about the entropy at room temperature, room pressure, stuff that you can look up in a table. So what we can do is we can use the table, so like less irregularities. Yeah, less irregularities because it's a nice perfectly formed lattice for diamond. So if you look at the back in the table, you can look up the entropies for graphite and diamond at room temperature and room pressure. So this is what they are. This is, of course, joules per Kelvin. Diamond, 2.38 joules per Kelvin. And so we see that from this, that the free energy for graphite will decrease faster with increasing temp compared to diamond. And so thus, the higher you make the temperature, it makes graphite even more stable compared to diamond. And so basically don't put your diamonds in fire, don't heat them up, because they will become less stable and they will convert into they'll convert into graphite much more quickly than they would otherwise. But yeah, again, it takes more than 1 billion years at room temperature for this process to occur. Okay, so that was just a little bit of fun, just thinking about these kinds of relationships between the free energy and the temperature and pressure for the specific case of graphite and diamond. Nothing too deep going on there. So one of the last concepts we want to discuss here is the so-called Clausius-Clapeyron equation. And I'm sure I'm just butchering that pronunciation because I think these are two French people, and we all know their pronunciations are wild. So what can we say? We know that the temperature dependence of the free energy is proportional to minus S, just like we said up here. And we also know that the pressure dependence of the free energy is proportional to the volume, which is what we just said on the previous slide right here. So those were both easily derivable from the thermodynamic identity for G. So what can we say? Well, we can say that the shape of the actual phase boundary on a phase diagram, on a PT diagram, that it has to be related to the entropies and the volume. It's telling us that the slopes, the ways that this depends on temperature and pressure is dependent on the entropy and the volume. So just knowing that, we should think that we can probably derive some kind of relationship that tells us what the slope is at the boundary of this phase relationship. Okay, so what we're going to do is we're going to specify the boundary between, for example, a liquid and a gas, but the distinction here is completely arbitrary, just phase 1 and phase 2. We're just analyzing some phase boundary. And we're going to consider a single mole. So we can use stuff in the book, for example. Okay, so what do we know about a phase boundary? What what is true at a phase boundary with respect to the Gibbs free energy? Do we have any thoughts about that? So if we're at the phase boundary, what can we say about the Gibbs free energy for the liquid phase versus the Gibbs free energy versus the solid phase or the gaseous phase? Are they maybe equal to each other? Yes, indeed they are. So if we're on the boundary, then it must be the case that these two things are equal because they're supposed to be equally likely at the phase boundary, right? So we can take the differential of this relationship. What about latent heat? What about it? Do you have a question about latent heat? I mean, we're about to get into like how latent heat can be thrown into this. So maybe your question will be answered, but I'm not sure what you mean, Jerry. So we can take the differential of this relationship. This is, again, just true at the phase boundary. Now what we're going to do is we're going to apply the thermodynamic identity. So what can that give us? Well, for G, thermodynamic identity is minus S dt plus V dP plus mu dN. All this time, we're just assuming that we're not changing the number of particles. So this is 0. So now what we can do is we can use this relationship and just apply it to both sides of this equation right here. So dGl and dGg, where L is liquid and G is gas, or just some states, it doesn't matter. So we can get that SL dt plus VL dP is equal to minus SG dt plus VG dP. So just applying this, the thermodynamic identity with it restricted to Tn is 0 to what we know about the phase boundary itself. Okay, so we can get the entropies all on one side. So let's do that. So we got SL dt plus SG dt, and we can move the volumes all onto one side. So subtract that over, Vg dP minus VL dP. And then we run out of space. We go to the next page. And we can write this relationship as minus SL plus SG dt equals minus VL plus VG dP. Just taking the relationship that was on the previous page and just simplifying it in terms of the differentials. Okay, so simple enough algebra there. What do we have now? Well, we have that we know we can just divide by dt to get the derivative of p with respect to t. That should be equal to SG minus SL all over VG minus VL. This is true at the phase boundary. Okay. So basically, if we know the difference in the entropy and we know the difference in the volumes, we can say what the slope is. So that's pretty interesting. So how would you actually use this? Well, if you had like a phase diagram, for example, like water. What does that look like again? Something like this. So it looks something like that. So basically at any of these boundaries right here, we can select a certain point. And if we can, for example, look up in the table, let's just say that this is at P is 1 atmosphere and like T is 300 Kelvin, so room temperature. Then we can look up in the table in the back. We can pick off the exact values for the two different entropies at that pressure and volume, or pressure and temperature. And we can pick off the volumes at that point, stick them into this formula, and it'll tell you what the slope is at that point right there between those two phases. And so you could iterate that, so you could find what the entropy is at a slightly different temperature and pressure and the volume. You can find it there as well, and so you could find all these different slopes, and then you could construct yourself a curve. So we're not actually going to do that, but that's how you could construct something like that. You could construct a phase space diagram. Okay, so in general, rather than writing it like this as the difference between two different entropies, we can also express this as in terms of the latent heat and the temperature. So we can write Sg minus Sl as L, where L is just the total heat here, the total latent heat, divided by the temperature. And be careful here, because when Schroeder talks about this in the book, he refers to this L as the total heat. But previously in the book, we had defined L, the latent heat, as the heat required for the transformation to occur divided by the mass of whatever substance we're talking about. So that is not the same as this L that he's using in the book right here. This L is simply the heat required to accomplish this transformation for a specific object. So just keep that in mind, that's not what's being used here. This is just heat. It's like Q. It's just the heat that's being required for this transformation. So if we use this fact, then we can use that in our relationship to derive the famous relationship, Clausius-Clapeyron relation. And so this applies to any phase boundary. That's what's so powerful about it. Any phase boundary. Okay. Let's see. So we could, for example, we could apply this to the diamond graphite example like we were doing before. So if we take 1 mole of diamond, 1 mole of graphite, if we take 1 mole of diamond, turn it into 1 mole of graphite, the change in entropy between those two different phases is going to be 3.4 joules per Kelvin, just pulling that out of the back at room temperature. And the change in volume for going between those two. So let me just say, let's say diamond to graphite. So these are just the quantities that you can get from the back. So this would be 1.9 times 10 to the minus 6 meters cubed. And so if we take those two, put them into the relationship that we had up here, we could get that dP over dt for the graphite diamond boundary is 18 bar per Kelvin at room temperature. So basically, you need a ton of pressure in order to actually go between these two. So yeah, that's all it's saying. It's just that the pressure has to increase a lot if you have a small change in the temperature. So making diamonds requires very high pressure, which we already know. Any questions about that? This is all pretty straightforward. Honestly, I don't think the class is really going to get much more rigorous until we get to chapter 6 again. This whole like chapters 4 and 5 is all pretty like hand wavy and qualitative, so just keep that in mind. All right. Anybody? Yeah. Mm-hmm. Mm-hmm. You're asking about what's happening in the in-between? Like in the process? Oh, no. I mean, when you're going from diamond to graphite, you're not passing through like some kind of intermediate liquid phase. It's a little bit more confusing exactly how to apply the latent heat to this example. It's easier to just look up the entropies for the two. The point is just that you can use this relationship if you know offhand what the latent heat is to accomplish this transformation. And I mean, we could use this fact right here to calculate what the latent heat is for this transformation if we wanted to. But there's just not really a big point to do that. Do you see how we would do that? We just take this, equate it to L over T delta V. We know T, we know delta V, so you could pick off what this actually is. But yeah, there's no like melting or anything going on there. It's purely just going from diamond to graphite. Yeah. Yeah, it applies to any phase boundary. So if you have a diagram that looks anything like this, where you're talking about like over here is like phase 1, over here is phase 2, it could be anything, phase 3. At any of these boundaries, this will always apply. You'll always be able to find the slope in that way. Okay? Yeah, so even for like the superconductors and everything, it'll all be the same relationship. But that's why this is such a big deal. That's why they got their names on a relationship. So if you do something like that, maybe you'll get your name on something cool like that someday. All right. Should we discuss this? So the last bit of chapter 5 is the van der Waals model. And the van der Waals model isn't like real. It doesn't actually represent anything that exists in reality, but it displays a phase change, which is the only reason he's talking about it. So I'm questioning right now whether I should show you or whether you're good with not seeing it. Do you want to see it? Can I take a little poll? Yeah, I see it nods. Okay, we're gonna see it. We're gonna check this out. Check it out. Okay. Van der Waals model. Okay, so just to make this super clear, this doesn't actually correspond to anything real. The only point of looking at this is that it's a model that we can build, which we can analytically show displays a phase change. Okay, so that's all we're gonna look to show. So if there are any weird things going on, chalk it up to the fact that this isn't real. So what we're gonna do is we're gonna describe the modification of an ideal gas law that can quote unquote apply to liquids. So what kinds of things do liquids obey that gases don't, basically? So, well, liquids. Okay, so relative to the ideal gas, we would expect that a liquid, its minimum volume is not 0. So for gases, we've always just let V range over whatever the heck we want. It can go to 0 if we want it to. But here, we're going to make there be some minimum volume. Okay, and so how can we accomplish that? Well, we can just take the ideal gas law, for example, and we can add an offset to the V there, just some constant offset. And that I should have said that earlier. Basically what we're doing with the van der Waals model is that we're modifying the ideal gas law a little bit to accommodate the kinds of features you would expect from liquids. Also, something about liquids versus the ideal gas is that they should exhibit some kind of short-range attraction. So at very, very close ranges, they repel each other, but at semi-short ranges, they attract. They want to be next to each other. They have cohesion. That's something we observe. So how do we incorporate this? Question. Well, let's consider the potential energy. So let's suppose that potential energy is the only thing we're considering for the moment. So, and we can relate potential energy to forces, right? Because from classical mechanics, we know that a force is equal to minus the gradient of a potential, right? So that's kind of where we're going with this. So we want to see how the potential actually behaves when we scale things in the system. So what will it do? Well, if we double the density, then each particle in the system will have twice the neighbors. So we're specifically doubling the number of particles while we're holding the volume constant. That's just what doubling the density means. So in this case, they'll have double the neighbors, and thus twice the potential energy overall. So basically how we can write this is that the potential energy due to a single particle in the system interacting, it should be proportional to minus n over v. Just the concentration. So if we want to count up the total potential energy of everything in there, we're going to define that as just normal U. Well, that's just going to be proportional to taking every single particle and adding up its potential energy contribution. So it'll just be the number of particles times the contribution from a single interaction. And so we get something that looks like minus n squared over v. And now we can recall that pressure is an energy density. So, okay, so pressure, its units, it looks like joules per meter cubed. So it's an energy density. So basically, we can modify the pressure term in the ideal gas law, P, by a term minus U, the one that we just calculated, over V, which just ends up being minus n squared over v squared. Sorry, that's minus, so we want that to be a plus. Plus n squared over v squared. So the van der Waals equation looks like this, just making those modifications. It looks like P plus a piece that takes into account the short range attraction times what is the now modified V, which takes into account the fact that we don't want there to be a possibility of going to zero volume. NKT. Okay, so we can get this into a nicer form where we only have it dependent on P. If we do that, we get the following expression, NKT over V minus NB minus AN squared all over V squared. Okay, so that's just taking this relationship right here and solving it for P. Oh boy. Okay, so what's the best way to describe this? So let's try drawing this graph that he has written in the book. Okay, so he's got a plot of P, the pressure, over the critical pressure, and I'll describe what that means in just a second, versus V over the critical volume. And so what I'm going to draw here are just a series of isotherms corresponding to this equation of state. So previously we understood isotherms in the context of the ideal gas law, right? So that was just if we took this equation right here without the NB and without this term, and we just held T constant and plotted what P versus V looked like. Well, in this case, it looks a little bit different. But what we call the critical isotherm is the one that looks like this. And the reason it looks, well, So this is a critical isotherm. And the reason it's the critical isotherm is because if you go just a little bit below that in temperature, then you get something that looks like this. So anything below that, it develops a little bit of a valley right here. And anything at the critical temperature or above the critical temperature is just completely concave up. So if you keep on going lower and lower in temperature, you get more of these looking things. And so the critical pressure and the critical volume are just the pressure and volume corresponding to this critical isotherm right here. So he just draws it in units of the critical pressure and critical volume. So basically, if you look at this and you want to try to decipher what's going on, well, basically, the reason you're seeing like this asymptoting right here as you keep on going to smaller and smaller volumes is that we've introduced a smallest minimum volume, right? So there's effectively a barrier right here where you keep on applying more and more and more pressure, but you're going to have to apply an infinite pressure to actually get it to there, right? So that displays what we were thinking before. And then this valleying thing is due to the short range attractive force that we described. Okay, so the thing that we want to show now is that this actually displays a phase boundary or a phase transition in a really, really simple way. So how are we going to show that? Well, we're going to use our Gibbs free energy thermodynamic identity. So let's take that out of our toolbox. dg equals minus sdt plus v dp plus mu dn. Okay, so let's hold n and t fixed. So in the case that we hold n and t fixed, we have that the change in the Gibbs free energy is just going to be the volume times the change in pressure. So if we divide both sides of this by dv, the change in volume, we can rewrite this as del g, del v, and we've held n and t constant, and going from there to there. But this will just be v del p del v with n and t constant. Okay, so now what we can do is we can take our van der Waals equation right here, and we can actually calculate what dp dv is for this specific model that we've built. So if we do that, del p del v with n and t held constant, it'll just be that on n kt v minus nb minus a n squared over v squared. Okay, so you take the derivative and you just get minus nkt all over v minus nb quantity squared plus 2a n squared over v cubed. Okay, so if we want just this side now, we just got to multiply this by v. So we have that v del p over del v, n and t held constant, just gives us minus n kt v all over v minus nb quantity squared plus 2a n squared over v squared. Whew. Okay. So that is just del g del v respect to n and t. All right. So now we can simplify this a little bit. So we can do the trick that he does in the book and takes v, writes it in a nice way. So write it as this plus nb. So v is equal to v. But that allows you to rewrite this relationship, del g del v, as the following. So I'm just taking the relationship I had on the previous page and applying this. So this would be v minus nb nkt all over v minus nb squared, then minus this term, nb plus nkt all over v minus nb squared, and then plus 2an squared all over v squared. Okay, so that allows you to cancel out that bit right there. Oh, hold up. There's no addition there, that's multiplication. Okay, so at this point, what do we want to do? Well, we want to solve for g as a function of volume. So you actually want to integrate this expression. So we could integrate it just by multiplying by dv, getting it over there, integrating with respect to g, and then integrate this expression with respect to v. So we'll do that without inserting too many details. So just taking this expression, that's just the dots right there, right? So if we carry out that integration, we can get that g, the Gibbs free energy, is minus nkt log of v minus n times b plus nkt times n times b all over v minus nb minus 2an squared over v, and then plus a function that depends on t. But we only care about the function of v, so just absorb all of that nonsense into this. Okay, so now let's try to understand how we can actually see this phase transition. So we're going to plot a single isotherm. So this is P over PC. This is V over VC. Okay, so let's look at an isotherm that looks something like this. And let's label the points on this isotherm. So we're going to go from 1 to 2. We're just going to keep on compressing it to 3 to 4 to 5 to 6 to 7. Okay, so this is just some isotherm that is below the critical temperature, right? So something interesting we can see from this graph is we can map it onto a graph of the Gibbs free energy versus the volume. So we can take this expression right here, and we can use the fact that we know V versus P for every single point along this isotherm, and we can then use this relationship for here to plot the Gibbs free energy at each of these points, basically. So this is going to be G, and we're going to plot this versus the pressure, just because that's how he also does it. And so if you end up plotting this out, it looks something like this. Got to be very careful here. Okay, so if you plot this out, point 1 right here corresponds to roughly this point. This is 1. Point 2 corresponds to this point. 3 corresponds to that point. 4 corresponds to that point. 5 to there. 6 is right on top of 2. And 7 is over here. Okay, so at this point, in order to actually understand why there's a phase transition, we have to remember how we rehashed the second law of thermodynamics in terms of minimizing this value of the Gibbs free energy, right? So basically, if we track this process right here, we go 1, 2, 3, 4, 5, 6, 7. Here we're fine. Move up to 2, we're fine. Move up to 3. All of a sudden now, you're in a state where there's another spot at the same pressure, but it has a lower Gibbs free energy, right? So basically, once you move even just the slightest bit off of 2, all of these states up here are degenerate with other states that are at a lower Gibbs free energy. And so the system overall, it wants to minimize this Gibbs free energy, right? That's the same equivalent statement as maximizing the entropy. So if it wants to minimize the Gibbs free energy, what that tells us is that all of the states that lie in this piece right here, in this cycle, they're all unstable states. So if we want to move between equilibrium states, if we want to discuss that, what'll actually happen is that we'll just zip around this loop real quick. We'll go straight to 6 from 2, if we're talking about equilibrium stable states, and then we'll proceed to 7. So this right here will just zip around and you go straight to 6. So what does that look like in terms of this graph right here? Well, you go 1 to 2, but then you just zip straight to 6. So there's effectively a discrete change, a discontinuous change in the volume in going from 2 around this loop back to 6. So what happens is that you actually see in this model, you get a point where you start encountering these unstable states, and that tells you that basically you're just going to go around this loop all at once. And so therefore the volume discretely and discontinuously changes from a value here to a value over here. So it dramatically decreases. And so at least in the van der Waals model, you can think of this dramatic decrease as being like initially you're in a liquid phase, like down here. And then once you zip around and come back to the same spot, now you're at a smaller, much smaller volume. So that's usually what we think of as a solid. So basically, this is displaying something that is akin to a phase transition between a liquid and a solid in a van der Waals model. Now, this is quantitatively complete nonsense, but it qualitatively shows you how you can construct a simple model that displays the kinds of phase transitions that we've been talking about. Okay? Is that enlightening to people? Maybe, maybe not. Yeah, I mean, the van der Waals model isn't really something to be talked about too much, George. It makes more sense. Good. My goal is that things make more sense when you come here versus when you leave, or versus when you came. So yeah, that's all I'm going to talk about with this, because I mean, at this point, we've already said, like, we can see the phase transition thing happening. So that's all I wanted to get out of this effectively. Cool. So that is chapter 5. We are done with the thermodynamics portion of this book, and now it's on to StatMech, the real fun. That's when it's going to start next week. Is everybody psyched? Get talking about Boltzmann factors and partition functions, and start talking about indistinguishable and distinguishable particle statistics. Ooh, it's going to be a good time, you guys. Okay, we're gonna have fun. There's only 2 chapters left, so it'll be good. No, I mean, this is honestly when it gets more interesting to me, because a lot of this thermodynamics, it feels very tenuous. It feels like you can't really get your grasp on it, right? Because you don't really have a whole lot of mathematical knowledge to actually be saying all the nonsense that you're throwing. So yeah, get buckled up for some real math, kind of. Okay, so that's all I got for everybody. I'll open up office hours. You can drop by, chat some more if you want. But otherwise, have a wonderful weekend, and we'll talk to you on Monday. Okay, thanks.